In this video, I'm going to introduce you to some of the basics from equilibrium. We'll also look at how to write an equilibrium constant for a reaction as well. Equilibrium is this dynamic state of balance between the rates of the forward and reverse reactions. It's very important you understand that this is a dynamic state. It is not static, all right? Just because you're in equilibrium doesn't mean things are not changing, even though the overall amount may not be changing, okay? There are still changes taking place, all right? You're in this balanced state, but changes are still taking place. Essentially here, the forward and reverse reaction are both happening at the exact same rate. So there seems like there's no overall change, but there is still this forward and reverse happening at the exact same time. Okay, the concentrations of the reactants and products might not change, but you're still having this changing taking place. It's just that everything is kind of balanced. All right, so that's this idea of equilibrium. It's not a static state. There still are changes taking place. It's just that the overall state is in this state of balance. All right, the idea that all reactions go to completion is completely false here. Many reactions actually are in equilibrium, and the forward and the reverse rates do occur at the same rate when we reach that state of equilibrium. So I know we've kind of been focused here that every reaction goes from reactants to products, and that's it. But realize here, many reactions are actually in this state of equilibrium, and they don't go to completion. We definitely need to understand this idea of equilibrium not being this static state. Equilibrium is actually a dynamic state. So let's look at the difference here between static equilibrium and dynamic equilibrium. In a static equilibrium, there would be no reaction taking place. If equilibrium was static, you'd reach a point where no reaction was taking place. Basically, all the product molecules would be product and all the unused reactant would be reactant. Essentially, this would be like two people with the same exact weight sitting on a seesaw and not moving at all. All right. This does not actually occur. Equilibrium is not static. All right. We said that equilibrium is this dynamic state. Basically, a reaction is continuing to occur. It's just that the forward and the reverse rates of the reaction here are exactly the same. So it's the equivalent of a person kind of standing on an escalator, and the escalator is moving down, and the person is, trying to move up, and you reach a point where the rate down is equal to the person's rate attempting to go up, so the person doesn't move. But there are still changes taking place. That person is not standing still. The escalator is not standing still. It's the same idea of like if you were on a treadmill, all right? You match the speed of the treadmill here, so you have kind of these equal opposing rates, but you're not standing still, okay? So equilibrium is this dynamic state, even though the overall change, there's no kind of overall change in this balanced state, but there are still changes taking place. It's just that they're kind of taking place at the same rate here. We need to be able to look at graphs like this and understand what's going on. So these are concentration versus time graphs. Notice here, if we're looking at the one on the left, at the beginning of a reaction, you only have reactant molecules available to collide and to actually start the reaction. So at the beginning of the reaction here, the concentration of the reactant molecules is very high, and the product is zero because there are no products that are there. And then once these reactant molecules start colliding, start forming product, you start to see here that the reactant molecules will go down and the product molecules will start to increase. All right. Once you get enough here of the product forming, that's when you can actually have collisions taking place between the products that would allow the reverse reaction to actually kind of occur here. But even in both kind of graphs here, the products are non-existent in the beginning, only the reactants are there. As the reaction takes place, the reactants decrease and the products increase. But eventually you reach this point, after so long, you have no change in the concentration. So we say that this is where equilibrium starts. And after that, the concentration of both the reactants and the products remain the same here. All right, they don't have to be equal to each other. It's just that after that point, you see there's no longer a change in concentration of the reactants. There's no longer a change in concentration of the products. So we're at this equilibrium state here. All right, so pay very attention to this. These are concentration versus time graphs. All right, at equilibrium, the concentration of the reactants and products no longer change and they remain the same. Notice the difference here between these two graphs, okay? The top one is a graph of the rate versus time, all right? As you start a reaction, you only have reactant molecules available, so the forward rate is going to be very high, and the reverse rate is going to be non-existent because you don't have any product molecules available to collide and react. And then over time here, the forward rate starts to decrease, and the reverse rate starts to increase. Eventually, you get to a point where those rates are equal. That's equilibrium. All right. When the rates are equal, you're at equilibrium. The forward rate is equal to the reverse rate. Right. But notice here the amount versus time graph, or very similar to the concentration versus time graph. The reactants are still high to begin with, and they decrease over time. The products are low to begin with, they increase over time, but they don't have to be equal here. All right. You get to a point where there's no change in the product amount, or there's no change in the reactant amount, but they don't have to be equal to each other. This is different. In equilibrium, the rates of the forward and the reverse are equal to each other. That's how you know you're at equilibrium. But in a concentration versus time graph, the amounts don't have to be equal to each other. The amounts just don't change for a period of time. That's how you know you're at equilibrium. So pay attention to these. You do need to be able to differentiate between these graphs. You do need to understand what's happening in each, and understanding there's a difference between the rates being equal for equilibrium versus the amounts not changing but not needing to be equal for equilibrium. Whether a reaction favors the products, which we would say lies to the right side. Essentially, if you're writing a reaction, the products are on the right side, or whether a reaction favors the reactants, which would be on the left side of your reaction, depends on a few things here. All right, your initial concentrations are important. Obviously, if you can have more collisions, you would have a faster reaction taking place, potentially maybe forming more products. The energies of the reactants and products are important. Nature prefers this minimum energy state, so that's going to determine whether you're going to the reactants or the product side. And basically, the degree of organization here of the reactants and the products is important as well. Nature prefers more disorder, okay? So these things kind of contribute here to whether a reaction will kind of go more toward the product side, or whether the reaction will go and stay more on the reactant side. All right, so you got to kind of look at all these different things to see where an equilibrium will lie. This brings us to the idea of the law of mass action and the equilibrium constant. The basic gist here is that if you look at the relationship between the concentration of the reactants and products for a reaction at equilibrium, that relationship is going to be constant. All right. So if we have our reaction here, you can see our generic reaction, A plus B going to C and D, but it's in equilibrium with each other. And you have the coefficients for that reaction in front in lowercase letter. If you wanted to write the equilibrium constant expression for that reaction, it would be Kc equals the concentration of C raised to the power of its coefficient times the concentration of D raised to the power of its coefficient in the reaction, all over the concentration of A to its coefficient times the concentration of B to its coefficient. All right, this is the equilibrium constant expression for this reaction. And we'll talk about how it's written here in a second, but you can see pretty much it's going to be products over reactants always. And this Kc in front, that stands for the equilibrium constant. So it can be written as a number of different things here. It might be listed as Kc if you were dealing with molar concentrations. All right. It might be listed as Kp if you had partial pressures here. We've already seen KSP in solutions. It stands for the solubility product constant. If you were dealing with acids or bases, it might be Ka or Kb, or if you're dealing with the ionization of water, it could be Kw. The key is we typically use K here to represent the equilibrium constant, but what's with K could change depending on what you're using. And it could even be just listed as KEQ to indicate, hey, look, this is your K and you're at equilibrium. All right, so don't be thrown by the letter there with K. The key is it's just indicating that you're writing an equilibrium constant expression here for a reaction. And the reason we can do this is because there is this relationship here between the concentration of the reactants and products at equilibrium, and it's going to be constant. All right, so we're going to talk about how you kind of write this expression on the next slides. Here are the first three general rules here for writing an equilibrium constant expression. So first, these concentrations have to either be molar concentrations or you can do partial pressures here for gases. So in theory, you could do like the pressure of C times the pressure of D all over the pressure of A times the pressure of B. Okay, so that's important here. You want to be in molar concentrations or partial pressures. So if you're in moles, you need to get it to, molarity here. And if you have gases, you want to be in pressures. The products are always going to be in the numerator on top, and the reactants are always going to be in the denominator on the bottom. That is key. It's always products over reactants here. You got to just kind of drill that into your head. The equilibrium constant is always products over reactants. The coefficients in your balanced equation become the exponents here in the actual expression. All right, so whatever number here is in front of A, that's going to be the exponent here in the equilibrium constant expression for A. So that's something that, again, you just need to work with this, and you need to remember to include those in your equilibrium constant expression. Two more rules here with the equilibrium constant expression. Solids and pure liquids are never included in an equilibrium constant expression because they can't change their concentration. If you have a solid or you have a liquid, their concentrations are not going to change. Only aqueous species and gas species here are included in an equilibrium constant expression. So if you have a reaction and you have a solid or a liquid in that reaction, they don't get included here in the equilibrium constant expression. So products over reactants, you would just ignore any solids or liquids. We only want aqueous substances or gases here. And that's a big thing that you really need to remember. And there's not going to be any units for your equilibrium constant expression. So you need to make sure you're following these rules as you're writing equilibrium constant expressions. And this is something you need to be able to do. For all of equilibrium, it also applies in acid-base as well. So you really need to be good with equilibrium constant expressions and be able to write them correctly. So here you can see a first example. We want to write the equilibrium constant expression for this reaction. So the reaction is given. The first thing I notice is that all of the substances are in the gas form. So that means I'm allowed to include them all in the equilibrium constant expression. You can only include aqueous species or gases here in your equilibrium constant expression. We call this a homogeneous equilibrium because all the substances here in the equilibrium are in the same state. All right, so they're all gases. So when we write this, remember it could be KEQ. All right, K stands for your equilibrium constant. It could be KC if you were using concentrations. If these were pressures, it would be KP. All right, the key is K is standing for equilibrium here. Remember, it's going to be products over reactants always, and you have to use the coefficient in the balanced equation in front of a substance as the exponent here for it in the equilibrium constant expression. All right, so products over reactants. So we have the concentration of H2O squared times the concentration of SO2 squared. Both of them have 2's in front, so that's why we're raising each of those to the power of 2. Remember, products on top over your reactants, concentration of H2S squared times concentration of O2 cubed. All right, they're all gases, so they all get included here in the equilibrium constant expression. Just note of how this is different from writing a rate. Remember, in a rate law, you'd have rate equals K times the concentration of your reactants. Remember, only the reactants were important in a rate law, and the orders had to be determined via experimentation. You couldn't just write the orders or write the exponents from the balanced equation unless it was an elementary step. That's different here in an equilibrium constant expression. The products are important, all right? The reactants are important, and you take the coefficients and you make them exponents in your equilibrium constant expression. So just be careful with that. They are a little different here, but you definitely need to be able to write an equilibrium constant expression correctly. Let's look at another example here. We have CaF2 solid in equilibrium with Ca2 plus 2F minus. This is known as a heterogeneous equilibrium because all the substances are not in the same state here. And notice there's a solid in the problem, right? Solids and liquids do not participate in your equilibrium constant expression, all right? So when we do products over reactants here, the only reactant is a solid, so there's going to be no reactants listed. Essentially, there's going to be no denominator here in your equilibrium constant expression, right? So when we write this, again, KEQ stands for your equilibrium constant at equilibrium. This more specifically would be a KSP. If you remember when we did KSP, you had the solid dissociating into its ions here in equilibrium. We were essentially doing equilibrium stuff when we were looking at KSP, and we never had anything on the bottom here because you always have your solid as your reactants. And the reason why there was nothing on the bottom is because when you write an equilibrium constant expression, solids and liquids don't participate in that expression. So this would just be KSP is equal to the concentration of the Ca2 plus times the concentration of F minus squared. Remember, the coefficient in the balanced equation becomes the exponent here for a substance in the equilibrium constant expression. So products over reactants, it's just that there's not going to be any denominator here because the reactant is a solid. So that's the basic gist of how you write an equilibrium constant expression. Let's go through and try another example here. You're more than welcome to pause the video, try it on your own, and then zoom ahead to see if you got it right. So we want to write this equilibrium constant expression for this reaction in terms of pressure. First thing you got to start, looking for immediately, checking the phases here. They're all gases, so they all get included here in your equilibrium constant expression. They're asking me to do this in terms of pressure, so it's not just going to be a KEQ essentially. It's going to be more specifically here a KP. So when we do this, it's going to be products over reactants. I know they're all gases, so they're all participating here. So I have, this time it's not a concentration, it's going to be the pressure of NH3, and it's going to be squared because of the coefficient there in front of it in the balanced equation. So that's my product all over the reactants here. So it's going to be the pressure of N2, and that's just going to be to the power of 1 times the pressure here of H2, and that's going to be to the power of 3. Okay, so this would be my equilibrium constant expression for this reaction in terms of pressures. And notice I showed that by using the P here in the problem instead of using the concentration brackets. And it's products over reactants. Pay attention to the balanced equation. Make sure you're only including gases and aqueous substances here in your expression. Let's try 2 more here to make sure you're getting the hang of this. I would say pause the video, do both of these, make sure you can get these on your own, and then when you rejoin the video, I'll have them completely solved, shown for you so that you can see how you did. So pause the video right now and try both of these. Okay, so these are the answers here for both of these. You can see I just did it generic as a KEQ for both, and I used concentration symbols, but it's products over reactants for each. Don't forget to pay attention to the coefficients here, making them the exponents for each of the substances. For the second one, the water was a liquid, so it does not participate in the equilibrium constant expression. Only gases and aqueous substances are included in your equilibrium constant expression. So make sure you can write an equilibrium constant expression, and you need to be able to do this perfectly, following the rules every time because you will do this a lot. Let's talk a little bit more about this equilibrium constant. So KEQ can be determined for either direction of the reaction. All right, you could determine a KEQ for the forward reaction. you could determine a KEQ for the reverse reaction. The key is the same substances will be favored whether you use the forward or the reverse. So if a reaction favors the products, whether you do a KEQ for the forward or the reverse, the products are still going to be favored. Okay, the concentration of your reactants and products at equilibrium will vary depending on initial concentration, but the key is KEQ will always be the same as long as you don't change the temperature. Okay, so you could change, the concentration of the reactants and products at equilibrium, depending on what your initial concentrations were, but that's not going to change the value of KEQ here. If you change the temperature, you will change the value of KEQ. KEQ also does not depend on the overall mechanism of the reaction, so how you kind of get there is not necessarily important. It depends on stoich and temperature though. All right, so that's important. If you mess with the stoich or you mess with the temperature, you can change KEQ here. All right, so very important to kind of remember, if you change the temperature, you will change the value of your KEQ for a particular reaction. All right, so that's something you definitely want to remember here. I just want to point something out in case you see anything with this. This is kind of an old school AP thing. I'm not going to make you do this or calculate this, but there's just something I want you to realize here. KEQ does not always equal KP technically. All right, there's this little equation here, and the only way KEQ and KP would be equal is if this right here was equal to 0. Essentially, this delta N is your moles of gas products minus your moles of gas reactants. So essentially what that means is if your moles of your products, which are gases, are equal to your moles of gases for the reactants, that will give you a delta N being 0, which means KQ would equal KP. All right, so I don't know if you'll see anything with this. I definitely don't plan on asking you anything about this, but this is something just to be aware of here. If you have a reaction and the moles of gas in the reactants and the moles of gas in the products are the same, then KEQ will equal KP. All right, just something I want you to be aware of. Don't worry about doing any math with it. That's kind of the takeaway here from this slide. Again, this is more of just an FYI. I'm not going to hold you accountable for doing the math with that equation. Just something to be aware of. If you notice for this particular reaction, the moles of gas reactants are 4 and the moles of gas products are 2. So they're not the same. So technically KEQ and KP would not be the same here. All right, again, I'm not going to hold you accountable for the math, just that idea of the moles of gas, products, and reactants being the same in order for Kc to be equal to Kp. So what does the value of Kq actually mean here? Well, it can actually give you information about the concentration of your products or reactants at equilibrium. All right, so if you have a K value that's greater than 1, all right, so basically a large K value. Think about this. In order to calculate K, you did products over reactants. In order to get a K that's greater than 1, you must have had a bigger value for your products, your top number. That's the only way you would get a number here for K that's greater than 1. Therefore, that means there's a greater concentration of your products. Essentially, the equilibrium lies to the right side or to the product side. So the forward reaction is favored. You're forming more products, all right? You have to think about this in terms of the equilibrium constant expression. Products over reactants, more products on top would give a K greater than 1. So therefore, if K is greater than 1, the products are favored. If K is less than 1 or a small k, that means your reactant concentration is going to be greater. The equilibrium lies to the left side, favors the reactants. Remember, if you do products over reactants, the only way you get a K less than 1 is if you had a greater number on the bottom or more reactants here. So you definitely need to understand this idea. You need to be able to look at a K value and realize it's greater than 1, the products are favored, or it's less than 1, the reactants are favored. And if you use your understanding of the equilibrium constant expression, this should really make sense here. So if you look at this picture here, you can kind of see that a very, very small K value, they're showing you here K less than 10 to the minus third, basically means you have a lot of reactants present and very little products here. If you have a very large K value, they're showing K greater than 10 to the third. That means you have a lot of products, essentially a bigger number on top. So you see you have a lot of products here and very little reactants. In this intermediate state, you kind of have maybe significant amounts of both here. Remember how we kind of talked about here that, we just wrote reactions and we showed the forward arrow and we just assumed every reaction went to completion? Well, the reason it seemed that way is because these reactions just had very large K values. They're products over reactants. There were definitely more products formed than you had reactants. So it seemed like the reaction went to completion, but in theory, there were still probably some reactants there. So the K value for those types of reactions that seem to go to completion are just very large. All right, you have a lot more products present. So when you would calculate K, you get a very high number here. All right, so in theory, all these reactions kind of might, appear to go to completion, but realize there probably could still be some reactants left over, just that a lot more products are present compared to the reactants. We can kind of change reactions here, and this will lead to some changes with the KEQ. Remember, we said that equilibrium can be approached from either side, either the forward or the reverse. So if you write the reverse reaction, all right, and you have the value of KEQ for the other one, you just take the reciprocal of KEQ to get the new KEQ. So if you have the KEQ for, say, the forward reaction, and you want to write the KEQ for the reverse, if you just take 1 over KEQ, you have the new value for your reverse reaction here. So let's look at an example. We have this example here, N2 plus O2 forming 2NO, and I have my equilibrium constant for the forward reaction here. All right, so it's 1.0 times 10 to the minus 30. I wrote my Kc here for the forward reaction, products over reactants. They're all gases. Pay attention to the coefficients here for the exponents. If I wanted to reverse that reaction, now my products would be the N2 plus the O2, and my reactants would be the NO. If you wanted to calculate the Kc here or the KEQ for the reverse reaction, just take 1 over the 1.0 times 10 to the minus 30. So when you do that, you get 1.0 times 10 to the positive 30th this time. Notice the reaction still favors the N2 and the O2 side. All right. When you're looking at the forward reaction, the Kc is very, very low. That means products over reactants, there's many more reactants present, so it favors the left side, the N2 and the O2. When you reverse it now, you get a very large number for the value of Kc. Well, that means the products are favored. Well, when we reversed it, okay, our products are the N2 and the O2 still. So it still favors the same substances, whether you're doing the forward or the reverse. Just realize here, if you do reverse a reaction and you have the Kc for that reaction, you need to do 1 over the Kc in order to get your new Kc for that reverse reaction. Just like KEQ changes with temperature, as we already said, stoic also changes KEQ here. So if you are changing a reaction by multiplying it by some number, basically what you do is you take KEQ and you raise it to the power of the number you are multiplying it by. So be careful here. Just because you multiply a reaction, say by 3, you're not going to multiply the KEQ by 3. You're going to raise the KEQ to the power of 3. Okay, the power of the number you multiplied it by. So same reaction here, this N2 plus O2 going to 2NO. We have the Kc written. Now we want to know the Kc for this reaction. Notice the only difference here is we multiplied this original reaction by 3. So you have 3 in front of the N2, 3 in front of the O2, but then a 6 in front of the NO. So if you wanted to calculate the Kc for this reaction, you would just take your original K and raise it to the power of 3 to get the new value here. All right. So it's very important that you understand anytime you multiply a number by a reaction, you have to take the Kc and raise it to the power of the number you multiplied by to get the new Kc for that reaction. If you have a multi-step reaction here, each of the steps will have a KEQ value. So just as you're combining and making these reactions add up to give you the overall reaction, you also have to combine your KEQ values. But in order to combine the KEQ values, you need to multiply all the KEQ values together. So be careful with that. You might be adding the reactions together to make up or to get to your new target reaction, but you have to multiply all the KEQs together to get your new KEQ. You're not going to add the KEQs together. You're going to multiply them together. So if you notice here, we have two reactions written here, each with their own K value. And then they gave you kind of a third reaction, and they said, okay, what's the K value? So you have to realize here, by looking at this, that all we're doing is essentially adding these reactions together here to get that third reaction. So if you notice here, if we kind of add these up, all right, anything on opposite sides of the arrows in different steps would cancel. So the N2 cancel. The O2s are on opposite sides of the arrow, so they cancel. And then notice all that's left here is your 2NO plus your Br2 forming your 2NOBr. So all we did was add those two reactions together to make this reaction. So if that's all you're doing, in order to get your K value for this reaction, you need to multiply the K values of those two together to get your new K value. All right. Even though you added the reactions together, you multiply the KEQs together to get your new KEQ. And you could be expected to kind of do this in problems in order to get a K value for a new reaction here. This is just a quick summary before we actually do an example here. So if you are doing the KEQ for a reverse reaction, you need to do 1 over the original KEQ. If you change the stoich here, if you multiply the reaction by a number, you need to take the KEQ and raise it to the power of that number to get your new KEQ. And remember, if you're adding reactions together here, you got to take the KEQs and multiply them together in order to get your new KEQ. These summary slides are very important because they make sure they kind of take the big ideas, just kind of get them all together here so you can make sure you understand what you're supposed to do here in these cases. Let's look at an example here. And I love these problems because they're basically like a little puzzle. All right. You're given two separate reactions here, each with a K value, and we want to find the K for this reaction. All right. So basically what you have to do is you have to figure out, okay, what do I need to do to these original reactions in order to make them add up to this? All right. Now, this is very easy to do when you see it kind of all listed together here, and you can kind of see, okay, I have to manipulate the top equations to make it add up to the third. A lot of times what happens is AP will include this in a problem, and in one part of the problem, you might be given this, or maybe you're given this reaction, and you have to find this. In a different part of the problem, you might be given this with this information, and then later on in the problem, they'll just present this reaction to you, and they'll be like, what's the Kc of this reaction? Well, you have to realize, oh, this reaction can be obtained by manipulating the original equations. It's easy to see here when it's kind of all together, but if this was kind of in different parts, different pieces throughout a problem, you have to realize, oh, maybe I can get this equation by doing something to the other equations and the other K values that were given in the problem. So just be very aware of that. This is something AP might do. I've definitely have seen it a lot of different times here. So again, it's very easy to see when it's kind of set up like this and you're trying to reach this target equation. But if you ever have a problem and they're like, hey, what's this K value for this reaction? And you're like, I have no information. It might be given to you kind of in the problem in different pieces. All right. So again, I said this is basically like a little puzzle here. In order to find the Kc for this reaction, I have to see what did I do to these original equations. So the first thing I notice here is I see that I have 2HF on the left side. Well, if I notice, the only place HF is in the original equations is right here. All right. Well, in order to make that be 2 on the left side down here, I'm going to have to multiply this reaction by 2. All right. But when I multiply that reaction by 2 here, remember, I have to raise the K value for that reaction to the power of 2 as well. So I'm going to rewrite this here. I'll have 2HF now in equilibrium with 2H plus 2F minus. All right. And then my Kc here was the 6.8 times 10 to the minus 4th. But now I'm going to have to raise it to the power of 2 because I multiplied the reaction by 2 here. Okay, so just realize your new K value is going to be 4.62 times 10 to the minus 7th for the reaction. So if I multiply reaction by a number, I take the K value, raise it to the power of that number that I multiplied by. All right, so then the next thing I notice here, remember, this is like a little puzzle. I see this H2C2O4 on the left, but then in my target equation, that H2C2O4 is on the right side, right? There's no number in front of it, so it's still the same amount. So it looks like I'm going to have to flip this reaction. And notice the C2O4 2 minus is on the right up here, but in the target equation, it's on the left. So I'm going to have to flip that reaction. Remember, when you flip an equation, you have to do 1 over the KEQ for that new kind of reaction you wrote. So when I flip this one, I'm now going to have 2H plus on the left plus the C2O4 2 minus in equilibrium with the H2C2O4 here on the right side. Okay, so I flipped the K, so that means I have to do 1 over the K value, so 1 over 3.8 times 10 to the minus 6th here. And when I do that, it's going to come out to be a pretty big number here. It's going to be 26,3157.8947 here. Okay, so that's my new K value for this equation. I flipped the reaction, so I have to do 1 over the original K value. So let's confirm that these now do add up here to my target equation. Okay, so remember, anything on opposite sides of the arrows in different steps would cancel, so the H pluses are gone. It looks like nothing else can cancel, so when I write what's left, I have 2HF plus the C2O4 2 minus in equilibrium with the 2F minus plus the H2C2O4. So I got the target equation. This is good. So that means now if I added up these reactions to get the target equation, I have to take my new K values and multiply them together to get my new K value. Remember, because we added up the reactions, you don't add up the K values, you multiply them together here. So I've already made my changes to the K value. That's important. You have to kind of take into account the stoic and the flipping here. I already got my new K values, so I'm going to multiply them together to get my brand new K value for this target equation. And when I do the math with correct sig figs, I get the Kc to be 0.12. All right, so that would be the K value here for my new target equation. All right, so you just got to kind of treat these as a little puzzle. Think about, what do I need to do to the target, to these original equations, to make them add up to this target equation? And then pay attention to what you would do to the KCs when you make those changes.